be posting a homework right after the lecture today. Okay, so it'll be like a few problems, 4 problems or so. They'll build on what we've been going through so far, and also based on the problem we're solving today. And I want to complete the problem we started last time, and we will then move on to the Frenet-Serret Frame and our general local coordinates, orthonormal coordinates. Okay, so from last time, I'm just going to draw the figure very quickly. Okay, the problem. So I had a fixed Cartesian coordinate frame. So this was the x-axis, y, and z, and the unit vectors are I, j, and k as usual. Okay, we have a fixed observer who is sitting at the origin of the coordinate frame. That's the pointer. And then we have this right circular cone of slant height L and radius R, base radius R. So here is the cone. Okay, something to keep in mind. So first of all, let me label the center of the cone as capital P. C is the point of contact of the cone, and so I have an entire line of the cone that is contacting the surface at any given instant in time. This length is L, capital L. Then the base radius is R. I'm going to draw that figure here. And I'm going to call the distance from point O to point P as h. Okay, so this is h, this is O, this is P, this is C. And I'm going to call this angle that is subtended by these two lines, h and L, as some angle beta. Beta, and we have cos beta and sin beta. So cosine beta is h by L. Right, common angles. So this is R by L. And we also have a relationship between h, L, and R. R square plus h square is L square. And the dimensions that you are typically given are the base radius R. This is given to us, assuming, okay? And then this is also typically given to us. Base radius, and then L is called the slant height. Okay. We were told in this problem that the instantaneous line of contact is rotating about the z-axis at a rate of omega. Okay, so the instantaneous line of contact. You have heard about this instantaneous center of rotation, right? Typically for two-dimensional bodies. This is just a line for a three-dimensional body. Okay? So this is rotating at omega about the unit vector k. And what we are supposed to do, and it's a rolling without slip. The cone itself is rolling without slip. The implication of that being, at any given instant in time, if the cone is rolling without slip, it means that the relative velocity between any point on the instantaneous line of contact and the plane of contact is 0. Okay, instantaneous center of rotation is obtained in that manner. So which means that at any given instant in time, at this particular instant in time when the ILC is parallel to the y-axis, all points on this line will have a velocity of 0 because it is in contact with a fixed ground. Okay, so we are assuming the xy plane to be fixed. Okay, so xy plane fixed. And what we are supposed to solve in this problem is, at this instant in time, when the instantaneous line of contact is coincident with the y-axis, determine the angular velocity of the body. Okay, so at this instant in time, when ILC is coincident with the y-axis, what is the absolute angular velocity of the body? Meaning angular velocity of the body with respect to a fixed or an inertial frame. Okay, that is the meaning of an absolute angular velocity. And as I mentioned the last time we met, we select 3 frames. The first frame is the fixed frame of the inertial frame, which I call as capital F1. Okay, so F1 is an inertial frame. Then we attach another frame to the instantaneous line of contact. And at this instant in time, the instantaneous line of contact is aligned with the y-axis. And if I attach an orthonormal frame or orthogonal frame to that line, then I'm going to have the following directions. We decided on this last time. I'm going to have, I call this as a unit vector E2 along the instantaneous line of contact. Then if I call this as E1, then the cross product of these two is going to be E3. Okay, so E2, and this is this we call as frame F2. Okay, so I'm going to call this as frame F2. F2 is E1, E2. This is a frame that rotates with the instantaneous line. With ILC. And at any instant in time, the E2 direction is telling me what the instantaneous line of contact is. Okay? So this signifies at this instant in time, instantaneous line of contact is coincident with the y-axis. At the next instant in time, this is rotating. And I did not say if it is rotating clockwise or counterclockwise. Let's say counterclockwise, CCW. My notation, CCW, counterclockwise. Okay, commonly seen, but just in case it is confusing. So this instantaneous line of contact frame is rotating about the Cartesian frame at a rate of omega. Which means that I know the angular velocity of F2 relative to F1, which is going to be omega in the K. Omega of F2. Does this make sense to you? we will make use of the symmetry of the body, and then we will draw a body frame. Okay? This body frame, I'm going to say, is a line that is drawn from, as one of the coordinate directions is a line that is drawn from O to P. It pierces through the circle that you're seeing, the base circle. So that's one direction. At that instant in time. Then the other direction is parallel to the plane of the base circle. I'm going to call that M hat. And the cross product of these two gives me the second in plane parallel unit vector, which is S. Okay, so I'm going to write this down. I'm going to call this as the B frame. Unit vectors are M hat, and S hat, and you can write, even these are unit vectors really. You can put a cap on top of them, the E1, E2, and E3. It doesn't make any difference to our lives. Okay? So this is M hat, N hat, and S hat, which is M hat, plus M hat, body frame. Where M hat and S hat are on the same plane. And N hat is always directed from the point O towards the point P of the base circle. Does everything make sense? Yes?
So because this is a body coordinate, will it rotate with the cone, or so is there an arbitrary point, or will it always stay like pointing up?
Oh, it will rotate with the cone. So the idea is this, okay? Why am I interested in this body frame is because I want to see. So I know the angular velocity of this line here, this line OC. It's omega along the z direction, right?
Yeah.
But what I want to find out is, okay, if I have a frame that is attached to the body, and if that frame is rotating relative to this E1, E2, E3 frame, which is going to give me the spin of the cone. That spin of the cone is always going to be aligned along this line from O to P, which is the reason for this third body frame really, the third frame really, and which is the next statement I'm going to be making. Sorry. Okay. So the third frame, I'm going to say, has a angular velocity which is not unknown. But this angular velocity is relative to the second frame. And I'm going to say that that is some rate phi dot, and it's always going to be about the n hat direction. Okay? So I'm going to draw it out here. So phi dot is called as the spin of the cone, which is unknown. Is the spin of the cone relative to the E1, E2, E3 frame. So frame F2. Which means if I write that as a vector, an angular velocity vector, then omega of B slash F2 is going to be phi dot about the n hat direction. And just to keep all results here, I'm going to write omega F2 slash F1 is omega k hat. And people in this row, can you still see the rank here?
Instead of F2 should be B, since n hat's not part of F2.
Say that again.
For omega B, with respect to F2, should that be B
So the idea is, I fix everything. Right? I fix the Cartesian frame, I fix the frame E1, E2, and E3, and I take this cone guy and then I start spinning it. It is obviously going to have a large amount of friction at this point. But I don't really care about that yet because I'm going to make use of the rolling without slip constraint later on. But if I just imagine taking this cone and then spinning it, where it is sitting, the direction of the spin is going to be about the line joining the point O and the point. That's always going to be the case. It's a fact of life. Because of the symmetry of the point. Right? So does this make sense to everybody? Good to ask questions. Please make sure you're clarifying it. Happy to stop. Yes.
Is there any reason you chose capital omega for the rotational speed of the body?
No, it is just given to me. That's all. So this could be, you can call it as some side orders, some variables. You'll soon see that we'll run out of variables as we solve bigger problems. Okay, so now I have three frames, one rotating with respect to the fixed frame F1, the other rotating with respect to the frame F2. I can now invoke our addition of angular velocities. You saw that last time, right? So I'm going to write that equation. I'm going to get rid of all of these guys and keep the figure. Okay? So we will invoke omega b with respect to f1, which is really what we are interested in. What is the angular velocity of the body? With respect to an inertial observer is omega b with respect to f2, f2 with respect to f1. This is something we proved last time. So we'll make use of this. So this is really what we want. Omega f2 with respect to f1 is given to us, capital omega about the k direction, which means that making use of the problem details, rolling without slip and all these things, we will have to figure out what this omega of b slash f2 is. To find out what we want, we need to know omega b slash f2 using the constraint of the problem. The constraint of the problem is rolling without slip. Rolling without slip. Which implies at that instant the velocity of point C as seen by a stationary observer is going to be 0. Okay, so this is d by dt of r C slash O seen by a stationary frame of reference, which I'm going to say is F1 for us, is 0. So this is a constraint of rolling without slip. And we will see, what exactly defines a constraint, what is not a constraint, using the idea of virtual work later down the semester. At this point in time, you just have to take my word for it. Okay, but it also makes common sense, right? If I'm rolling without slip, it means that my relative velocity at that contact point is 0. If my relative velocity is 0 with respect to a fixed surface, what's my velocity at that instant in time? It's also 0. Okay? Alright, so based upon all the information that we are given, how do you solve this problem? Here are the elements of how to solve this problem. So somehow I have to invoke this equation. Somehow I have to invoke this equation also somewhere. So what I figure out is this, okay, Many times, when you start a problem, we don't know what to do. You don't know where to start. That's a very common issue in dynamics. And so I start doing what I know best. I start doing kinematics. And I say, okay, let me see, first of all, what the position vector of point P is relative to point O. And let me bring the point C into play as well. I'm going to write that down. To start off, with the position vector of point P relative to O, make use of vector addition. R P slash O is R C slash O, and R P slash C. So by doing this, I'm bringing all the frames into the picture. Okay? So this is with respect to a fixed observer. It is R P slash C. This is just basic vector addition. And immediately I see that, okay, hey, if I differentiate it on both sides, then probably this creature is not going to play much of a role because of the condition of rolling without slip. Right? So let's differentiate. Differentiate it with respect to an observer sitting on frame F1. Right? So d by dt of R P slash O with respect to F1 is d by dt of R P slash C with respect to F1, and then the constraint that's coming into play of C slash O with respect to F. Make use of the rolling without slip constraint, so we get rid of this guy. So we've made use of one of these things. Then I start looking at each of these terms. Okay, so let's first of all look at this one. So let me call that as term 1. Term 2. 1 is d by dt of R P slash O with respect to F1. What is my intention? My intention is to bring the body into the picture. So I'm going to write this rate of change using the body and then taking the angular velocity of the body with respect to the frame F1. Okay, so this can be written once again, something we proved last time. This is d by dt with respect to the body. This is a choice that you can make. I can write this with respect to the frame F2 as well. If I choose it with respect to the body frame, then here I have to write this as omega of B slash whatever frame I'm doing the time derivative in, cross with free slip. Why am I doing this? Is because I want to bring the body frame into the picture. Okay. Take this guy. Let's deal with that creature separately. d by dt C slash O with respect to the body frame. R P slash O, I can write it using the unit vectors of the body frame, isn't it? It is just essentially that H along the n hat direction. So let me write it out that way. We'll see the reason for that. And if I do the product rule here, this is going to be d by dt of h n hat plus h times d by dt of n hat. What is this first term? 0. Because the height h is a constant. As you can see from the geometry there. What is this term? I'm sitting on a frame and I'm saying what is the rate of rotation of that frame. Obviously I can't sense anything. So which means that is also 0. This term is also gone, so which means that good news, this entire term is gone. Which means 1 leaves me with the following. d by dt 3/O f1 is omega b/f1 crossed with the position vector or p/O, which I'm going to write in terms of the body frame vector. So this is going to be h. Running out of space. And copy these results and write them down here. So then beta is h by L, L, h square is r square plus h square, and I have these two things as well. So this is omega a hat phi dot n hat. So I'm just copying whatever I have on this. Okay. Okay. So then let's handle the second term. The exact same way that we handled the first term. Once again, bring in the body frame into play. So term 2, d by dt p/c. This is split into two parts. One is with respect to the body frame, because I want to bring that creature into play. This is d by dt with respect to b. Omega cross position. Am I making sense to everybody? You see the strategy for solving this problem? If you don't know how to solve the problem, start off with the kinematics. Try using the information that you have into the kinematics of the problem. Okay? So in many problems there is no particular exact approach to solving the problem. You have to attack it from different angles. It's almost like a research problem, right? You don't have a straightforward path to the solution. This term here, can anybody tell me? P/c. I'm sitting on the body and looking at the rate of change of that term. Obviously that's going to be 0, or if you want, you can write it this way and then prove to yourself that it's 0. Because I'm not going to do that. That's 0. So term 2 leaves me with the omega b/f1 or p/c. I'm going to use, once again, because of the fact that I've used the body frame to write that out, I'm going to write this as a little capital R in the m hat direction. Okay, so now we are talking. It's almost there. Obviously this is 1. 1 is equal to 2. shows me this cross product is the same as that cross product. So omega b slash f1 cross with n hat is. Alright. And now this is just geometric manipulation, vector manipulation, that's about it. We make use of the second useful result that we have written in this board, this one here. So omega b slash f1, I'm going to write it as phi dot in the n hat plus omega in the k. So this is phi dot n hat omega k. Right, does this make sense to everybody? And omega b slash f1 on the right hand side is also the same thing. Phi dot n hat omega k cross. Now we have to do the cross product, but you will immediately realize that the k hat direction is not on the same unit vector system as the n hat, m hat, and s hat system, which means we have to do a coordinate transformation. Okay. So first things first, I'm going to expand this cross product. N hat cross with n hat is 0, so that term vanishes. So I'm going to end up with omega times h k hat cross with n hat, which I don't know at this point in time. This is equal to, watch this, n hat cross with m hat is going to give me the third vector of the system, which is s hat. So this is going to be r phi dot s hat and r omega k cross with hat. And obviously you can see that in this equation phi dot is the only unknown. So if I find phi dot, then I know the angular velocity of the cone, entire surface. Okay. Now my question to all of you is, are you all familiar with coordinate transformations? Some. So for this problem, let me do it carefully. Then in the future problems we will go a little faster. Okay. So first things first, if I'm looking at the unit vector k hat, I know that k hat is perpendicular to s hat. So obviously it's not going to have components along this line. That's the first thing. So which means that if I say k hat, it will have components along m hat and n hat. So here is what I do. I can translate vectors, no problem, without changing their magnitude and their direction. So I take this k hat and I just come and draw it out here. Call that as k hat. And I'm going to draw my cone system now with all the angles and so on. So look at this. This is n hat, k hat, m hat. This is the point P. We call that angle as the angle beta, right? Because this was the point O. This was the point C. So if that angle is angle beta, then by geometry you can prove that this angle is angle beta. And essentially what we are doing is I'm taking this unit vector k hat and I'm projecting it onto the directions that I want to decompose this into. It makes more sense for me to go from k to the mn system rather than transform n to the ijk system. You can do either. Both ways are perfectly fine. It makes more sense to go from k hat to the m and n system because there is only one transformation I need to do. Okay? So if I look at this, I just drop a perpendicular here, a perpendicular there, which means I'm looking at the projection of these. Projection is nothing but the magnitude of the vector multiplied by the cosine of the angle between the two directions. So this is going to be the magnitude of k hat multiplied by cosine beta, and this guy is magnitude of k hat cosine of 90 minus beta or sine beta. And so k hat can be written. So k hat has a component along the m hat direction, which is going to be the k hat magnitude times cosine beta. Magnitude of a unit vector is 1. So this is going to be cosine beta. Direction of that component is positive m hat. The direction of the other one is positive n. Does this make sense to everybody? Are there any questions? So this is what I mean by coordinate transformation. So it's quite silly really. All we're doing is just projecting it. But once things become more three-dimensional, it will become a little more sticky. Okay? We'll wait for that bridge to cross. Now all I have to do is substitute into this vector equation, do the cross products, and then complete the problem. Let's do that quickly. Substitute omega h, that's the scalar quantity, k hat crossed with n hat. I'm going to have cosine beta n hat, sine beta n hat crossed with n hat. These are all the terms on the left hand side. Right hand side of phi dot s hat, and then r omega times cosine beta m hat crossed with m hat. Is my writing legible to everybody? These last few letters, all I'm doing is just substituting stuff. Maybe I'll just write it on the next line. This is plus omega times cosine beta m hat sine beta n hat. I'm going to get rid of this board now because we've done a big chunk of work. I was a bit hasty. I shouldn't have erased some portions of it, which I will foolishly rewrite again. That because I have all sines, cosines here, right? Alright, so let's do the cross product. Obviously, this term is not going to contribute. Everybody sees that, right? N hat crossed with n hat is gone, so I'm just going to get rid of this guy. Likewise, m hat crossed with m hat, this term is gone, so I'm going to get rid of that. I have my triad, n hat, m hat, s hat for my cross products. So this is omega times h, cosine beta, m hat crossed with n hat is going to be minus s hat. Okay, so this first term is minus omega h, cosine beta, s hat. Or find out s hat. write that creature in. And then the last one, r omega sine beta n hat crossed with m hat is by definition s hat, which we have just written there. So this is plus r omega sine beta. And because of the fact that they are all in the same vector system, because there is only one unit vector in this situation, I can now equate the component on this side as the sum of the component of this side. Okay? So let me do that next. So that's minus omega. Watch this, h. Cosine beta, instead of that I'm going to write it as h by L. Now I'm equating the components, so I'm not going to have the s hat coming into the picture. Okay? This is equal to r phi dot plus r omega. Sine beta is r by L. Bring the omega terms on one side, the phi dot on the other side, so I have r phi dot is minus omega is a common factor, L is a common factor. This is just h square plus r square, which is L square, or I have minus omega times L. So that phi dot minus omega L. And so this essentially says that, when I chose to write the direction of phi dot, I said it was along the positive n hat direction. That's not necessarily the case. This is spinning in the clockwise sense with respect to the body frame. So this tells me that omega v slash f2, which was this phi dot n, is minus of what I thought it was to begin with. So that the net angular velocity, which we wanted to find, is omega f2 slash f1. You write it out, this is omega minus omega L by R in the n hat, and then capital omega k hat. This is the net angular velocity of the body with respect to a fixed observer or an inertial observer. And in many situations, this is the actual start of the problem in dynamics. Because you need to get all of this information to actually do the kinetics of the problem. Where you do the sum of the forces and the sum of the moments. And one can substitute for k hat. It's of academic interest. And bring them all into the same unit vector system. That's completely fine. I'll just leave it like that. Okay? So this is a taste of things to come. Hopefully this piques your curiosity. It's not an easy problem, but if you have seen a problem of this nature once, then you have a strategy for handling problems of this nature in the future. And that's how we typically go through this entire course. Okay? So a lot of this information, to some of you may seem alien, but once we are done with it, you'll be thoroughly familiar. If you have questions, I'm more than happy to. End of this problem. Any questions? All of you are comfortable with the pace of writing on the board and so on. You write a lot of information on the board. I also keep erasing and going back and forth. Hopefully I have a flow that you can see. If there is any issues, please let me know. on to the Frenet-Serret Frame. Typically called the Frenet-Serret, but I think the other person, Joseph Serret, also contributed to it, so I would like to attach their names together. You've seen this before. This is just your tangential normal system, but we won't be calling it by that particular name anymore, okay? Because I can define a tangential direction based on my convenience. If I'm looking at a surface, I have an infinite number of tangential directions on the surface. Okay. So what I want to do is, first of all, why are we doing this? In many problems, you may know the path of the particle beforehand, a priori. For example, you're designing a roller coaster. You know the path of the particle to begin with. All you need to know is how the dynamics take place along that predestined path or predetermined path. And when you're solving problems of that nature, this is the best way to solve. So this is a strategy to tackle problems whose path is predetermined for them. It could be bodies, rigid bodies, it could be particles, it could be systems of particles. Does not matter. You can handle them all the same, all the fine by this particular way. Okay, so useful for describing motion along a predetermined path. And once we get into the basics of it, we will start looking at a classical problem. In 2D to begin with, we will look at a bead on a parabolic wire, and then we will slowly say, okay, I've done the two-dimensional work, I'll go to a three-dimensional problem, and start looking at a bead on a conical surface. How is the motion of this developed? What are the equations? Okay? All right, so, definition. Fixed coordinate frame. Bear with me, I will call this fixed coordinate frame by the unit vectors Ex, Ey, and Ez. Okay, so this is capital X, capital Y, capital Z, so this is the fixed frame. I'm now going to consider a space curve. It's a curve in space. Could be the trajectory of a particle, could be the trajectory of the center of mass of a body. Could be anything. Right? So this is a space curve. Belongs to R3 and so on. So this is a three-dimensional curve essentially. And I'm going to consider 2 points very close to each other. At 2 instances in time. Okay, so just some point P at some time T. Point P at some time T plus dt. I have position vectors from the origin all the way to these 2 points. First position vector, I'm going to call it as a position vector R. You've seen this before. Second position vector is R plus dr. Some small increment in the position vector value, which means that the third position vector that joins the 2 points together from the first one to the second one is dr. And we define the first Frenet-Serret formula as a form. This is the definition of the tangential unit vector. sometimes called the tangent basis vector, because in certain problems, especially when you go to plasticity theory and so on, the vectors that you define need not be unit vectors, depending on what kind of a coordinate system that you use. Okay, but we will not be having such issues. So the first formula, we will say that E suffix t, which is the tangential unit vector directed from the point P to the point P plus P at T plus dt, is dr by ds, where ds is the magnitude of E. So this is the first Frenet-Serret formula. Second one is also a definition. This is a definition. What we are essentially doing is this. To define a system of basis vectors, or to define a system of unit vectors, you need to define two. The third comes as a cross product of the two. So I'm defining the first one as the tangential unit vector. The second one I'm going to say is the following. I'm going to look at the variation of the tangential unit vector as a function of the space curve, det by ds is a variation of this unit vector as a function of the position along the space curve. By definition, any vector is its magnitude. Multiplied by the direction of det, as you know. And any vector is its magnitude and its unit vector along its direction. Do we know something about the direction of det? We derived this result sometime back. What is the direction of det? You don't need to specify a label, you can just tell me in general. Is it 60 degrees to ET, or 72.5 degrees to ET, or 180 degrees with respect to ET? Is it along ET? Perpendicular to ET. That's it. That's all we need to know. This is perpendicular to ET. We derived this, and we didn't derive it for det, but we derived it in general. Okay? And I'm going to call that direction perpendicular to ET, define it as the second direction, the normal direction. Define. As En, so this is the normal unit vector. And what we are doing essentially is going into differential geometry or surface geometry. This is all elements of surface geometry and screw theory and all these things. We will not go into the details of some of those things. We will stop at whatever is useful to us. Okay? One can dig very deep into this and take a whole course of this. I'm going to define that magnitude term. Det by ds to be a term called kappa, the Greek letter kappa, where kappa is called the curvature of the space curve. And by definition, curvature is defined as the failure of a straight line to be a straight line. Makes sense, right? It is defined as the failure of a straight line straight. And so we have the second formula. dET by ds is kappa. If kappa is 0, it's a straight line. If kappa is non-zero, it is not a straight line. And depending on the fields that you are working in or you're interested in, if you're in mechanics, kappa can take either a positive or a negative value. If you're doing surface topology or differential geometry, kappa takes only a positive value. In dynamics, we will assume kappa to be a positive quantity all the time. Okay? So we will assume this to be positive. For us. Alright, so we are getting along. Third one is easy. We define the third unit vector of this triad as the binormal unit vector. E suffix b. And this is defined as the following. Third Frenet-Serret formula. EB, ET, cross. And so the first three formulae, I'm just going to recap them here. You already have them everywhere on the board. So EP is dr by ds, kappa, dn is det by ds, and then eb, et cross. Common example of where we might see these kinds of frames. I can take a particle traveling along a cylindrical surface. Okay, so let's say that this is a cylindrical surface. Okay, this could be, for example, the middle surface of a cylindrical shell or a roof panel of some sort. And let's say that you are drawing, taking a marble and placing it on top of this roof panel, and depending upon the orientation, it is going to start rolling in one direction or the other. Depends on the forces that are acting on it. You can obtain its equation of motion. Before doing that, we define a local coordinate system using the Frenet-Serret triad in the following manner. You construct what are called as the coordinate curves. So if I call this direction as the z direction, so this is, I guess, x and y, x, y, and then z is into the page, which means that if I draw vertical lines, if I draw lines along the length of the cylindrical panel, these are lines for which, if I, let's say that I'm sitting, this is my observer here. If I use an angle theta to define where I am on one of these lines, you will see that these are lines of constant theta. Does this make sense to everybody? These lines here are lines of constant theta. Okay? Or these are called as the z coordinate curves. These are lines of constant theta. So those are the Z coordinate curves. So this is a net. You can see this is another line. This is another line, and so on. And I could have lines of constant Z as well. You invariably see that, right? If I look at one of those curved lines, then that's a line of constant Z. These are called as the theta coordinate curves. And what we typically do in dynamics, in rigid body mechanics, and even in deformable body mechanics, you can, at any point which is an intersection of these coordinate curves, you can draw a base vector system. Okay, so this is an intersection of the two coordinate curves, right? One along what is called as the axis of the tube, or the axis of the shell surface, which is called as the generator direction. Okay, so this is the generator direction. Generator lines, and the intersection of that with the theta coordinate curve, that's a material point on the surface of the shell. On that material point, I can define a coordinate system, a tangential direction. Right? Look at this. I can define another direction that is also tangential but along the generator direction. And in that instance, this is actually going to be a binormal, because if I do the cross product of ET and EB, so if I write the triad, this is ET, EB, transfer EN, EB. If I do the cross product of EB and ET, I'm going to have a normal to the shell surface, which is pointing towards the center of curvature. Okay, so that's going to be pointing inwards here. So in reality, it should be somewhere here. So this is going to be my normal direction, and depending on where I am sitting, if I'm here, I have a different tangential direction, binormal, and a normal direction. So you can see that this is a local coordinate system. At each and every point, the directionality of these need not be the same. They will be traveling along the surface of the shell. In rigid body dynamics, when we start out, these will be orthonormal unit vectors. And because of the fact that our rigid bodies do not deform, in subsequent configurations of the body over time, they will still remain orthonormal, which is indeed a blessing. Because if you're looking at mechanics problems, plasticity, deformations, and so on, these coordinate frames themselves will start deforming with the body. And they need not end up being orthogonal to each other, let alone orthonormal. So that's the other situation, other side, the darker side of the cave, which we are not visiting yet. So for us, if they start off as orthonormal, they will remain orthonormal, which is very great. Okay? So this is just an example of where you can use this. I'm going to go forward. Any questions, please? And in mechanics, deformable body mechanics, these coordinate systems, this is a curvilinear coordinate system, and they're called as a convected curvilinear coordinate system because they convex along with the body, and they deform along with the body. And they are an integral element of understanding strain, finite strain deformations, okay, finite rotations, and so on. Okay. Two more formulae which will cap off the Frenet-Serret frame, and then let us solve some problems are the following. So I have 1, 2, and 3. What's this? 3. The fourth one, I'm going to look at dEb by ds. And obviously the next question is what is den by ds? we already